Hello everyone, welcome back. So we'll continue the discussion of the wave equation in more than one space variable. In the previous class, we derived a formula for the solution of the wave equation in three dimensions, which is called Kirchhoff formula. And now we use the same to derive a formula for the solution of the wave equation in two dimensions, and this is known as method of descent and it's due to Hadamard. So we'll start discussion of the two-dimensional wave equation. So in the previous class we also using the Kirchhoff formula we observed some qualitative properties like domain of dependence of the solution and range of influence of the initial data and Huyghens principle, etc. Okay. So now we start discussion of the wave equation in two dimensions. So we use some temporary notations here. So we write Laplacian sub 2 for the two-dimensional Laplacian and Laplacian 3 for the three-dimensional Laplacian. So we'll be going from two-dimensional to three-dimensionals, etc. So first we'll make some simple observations. So if u, which is equal to u of x1, x2, xt, satisfy the two-dimensional wave equation, okay, so we can treat this u as an independent function of the x3 variable, so it also satisfies the three-dimensional wave equation. Okay, so we can just take that u is independent of x3, so this del square u by del x3 square will be 0. Okay, and conversely, if we have a solution to the three-dimensional wave equation, right, v of x1, x2, x3, t, then if I restrict to the plane x3 equal to 0 or any constant, you can put that, okay, and then this restricted function, now it's a two-dimensional thing, okay, so this u satisfies the two-dimensional equation, two-dimensional wave equation. Okay, so these are the simple observation. So we are now going to construct a function which satisfies the three-dimensional wave equation, and by this restriction we obtain the formula for the two-dimensional wave equation. Okay, so now you consider the initial value problem, two-dimensional thing. Okay, so as observed here, so this, if we define this v of x1, x2, x3 t equal to this u of x1, x2, x3, so that satisfy the three-dimensional equation, and its initial data are again independent of the x3 variable, and they are the initial data of the function u, which we are looking for a formula. Okay, so now that we satisfies the three-dimensional wave equation, okay, and now we find that formula for the solution of this three-dimensional wave equation using Kirchhoff formula, and then we recover our u by putting x3 equal to 0. Okay, uh, okay, maybe little read here. Okay, so this first you write this formula for the solution of the uh, so let me just write that. So use Kirchhoff formula for V of x1, x2, x3t. Okay, using this initial conditions which are independent of x3 variable. Okay, and again in the we are more interested only in this V of x1, x2, 0t. Okay, so you go back to Kirchhoff formula, which is okay. So this yes, this is the Kirchhoff formula now. Okay, so this is a two-dimensional surface integral in 3D. Okay, so that's so we use slightly different notation here. Okay, so not to be confused. Okay, so let's write down the expression for V of x1, x2, 0t. Okay, using Kirchhoff formula. Okay, so for the so this is nothing but, so let me again stress that, so this is nothing but V of x1, x2, 0. Okay, so this is surface integral in 3D. Okay, so over this sphere. Okay, and as the integrand, this psi of y1, y2. Okay, just observe this one. So this does not depend on y3. So we write this surface integral as a two-dimensional integral, and that is easily done. So look at this surface. So I am using here y tilde. This is, yeah, I have written here. So this is in 3D. Okay, and there is no x3 here because we are taking x3 equal to 0. So it is just y1 minus x1 square plus y2 minus x2 square plus y3 square, and that's equal to c square t square. Okay, that's we are on that surface, right? So we convert this surface integral into a double integral, and that is easily done. Okay, so we rewrite this expression as y3 square equal to c square t square minus y1 minus x1 square minus y2 minus x2 square. And so if you recall how the surface integral is defined, so now this one, so as y1 and y2 vary over this circle, okay, so y3 covers this sphere, and so there is one upper hemisphere and there is lower hemisphere, and both contribute the same amount to this integral. Okay, so suffice is to consider just one integral. The other one is also very similar except for this time derivative. Okay, so how do you compute this surface measure? Okay, so some surface measure simply is this formula. So that's a double integral. So if you simplify this, so using this expression for y3 square, you compute this del y3 by del y1 and del y3 by del y2 and do some simplification. It turns out to be Ct by mod y3. Okay, again y3 can use that square root. Okay, and this y1 y2, they are in this circle now. Okay, circle centered at x1 x2 and radius Ct. Okay, so this surface integral, forget about this constant for the time being. So this surface integral is nothing but twice, as I said. So there is one upper hemisphere y3 positive and y3 negative. They contribute the same amount, so that's why it's 2 here. Okay, and so this now it's a double integral. So let me just stress that. So it's a double integral. Right here also. Okay, and y3 I am replacing by this expression. So y mod y3 is square root of c square t square minus those two terms. Okay, so let's write that in a simplified form. So let's write that as r square. So r square is nothing but y minus x square, which is y1 minus x1 square plus y2 minus x2 square. So note that this is this exact, this is just ball centered at x and radius c. So x is here, just x1 x2. Okay. So similarly for the other integral, so I replaced by phi there. So we have another one here. So if you put back all this this expression, so now we have converted this surface integral uh, and written as double integral, and finally we obtain this solution. So in the three-dimensional case, the Kirchhoff formula involved a surface integral. Okay, so it's, but in the two-dimension case, so you already start seeing the difference. So this uh, integral r over the ball. R over. So it is not circle, but the ball. So let me just write that. So this there is x and this radius is ct and the integral is over this two-dimensional object. Okay, and that makes the domain of dependence and other qualitative properties very much different uh, from the three-dimensional solution. Okay, so for example, this is the domain of dependence. I just mentioned that. So we are interested to know how the value of the solution at a point u of xt for t positive depends on the data on the initial line t equal to 0, the initial space t equal to 0. Okay, so this is t equal to 0. So we are interested in knowing uh, how is this dependence of u on the initial condition. Okay, so if again look at the formula, so we require that entire ball. So this is x here, so x 0 t equal to 0, and this is the, so this radius is ct, and this entire disk now. Okay, earlier in three-dimensional case it was only the sphere, the circumference. Okay, so similarly you can write down the range of influence, etc. Okay, and now let us see so the support of the solution at a time positive. Okay, how it depends on the support of the initial data. Okay, so again assume that support of phi and psi are in this ball of radius rho centered at origin, and similar calculations will show you that the support of the solution is contained in C, rho plus Ct. Okay, so this is all we can say in the two-dimensional case. Okay, so just we cannot say anything further because of this integral which depends on the entire disk. A physical situation, simple physical situation depicting this two-dimensional wave propagation. So consider a large lake, and if you throw a pebble in the water under calmness conditions, that wind is not blowing and other things, so you see the waves never vanishing, though their amplitude will become smaller and smaller, but they will never vanish, and this we call this Huyghens principle again. Okay. In the weak form. and as we see little later uh, that this persists in all even dimensional case. Okay, so this is only n equal to t how we have done here, but it's a this Huyghens principle in the weak form persists for all even dimensional wave equation, and Huyghens principle in the strong form persists for all odd dimensional wave equation. Okay, so there is another interesting application of this method of descent uh, to the telegraph equation. Perhaps I will come to that point little later. So now let's discuss the inhomogeneous equation. So if you recall, in the first part of this course, we have done this in detail uh, for the one-dimensional wave equation, and same principle holds here. So again IVP, so UTT minus C square Laplacian U equal to, now take a function on the, so this is usually called forcing term or inhomogeneous term. Okay. So this x in Rn, so let me just write that, though we have derived formula for only n equal to 3 and n equal to 2. Okay, so but this principle holds for all the dimensions. So this is also refreshing of what we have done for the one-dimensional wave equation. So this is what we are now describing is called Duhamel's principle, and it's a very useful tool in obtaining a solution of the inhomogeneous equation from the knowledge of homogeneous equation. Okay, not only for the wave equation but many evolution equations, even including heat equation. Okay, so first observe, so we exploit linearity. Okay, so we consider two problems. So one is inhomogeneous equation with zero initial data. Okay, and another one we consider homogeneous equation. So let me use that W. Now homogeneous equation but with general initial conditions. Science. So we split the given initial value problem, so inhomogeneous equation and arbitrary initial conditions, into two problems. One inhomogeneous equation with zero initial data and another one homogeneous equation with given initial data. So phi and psi appear here, and this is same as this f. Okay. So using linearity of the equation, it's very easy to check that. Then u is equal to v plus tau. So whenever there is linearity, we will always try to exploit and uh, generate simpler problems to solve. Okay, so this one, at least for n equal to 2 and 3, so this solution is given by Kirchhoff. Okay, so it's sufficient to consider this inhomogeneous equation with zero initial data. Okay, and for that we apply Duhamel's principle. Okay, so thus consider, again let me go back to thus consider the simpler IVP. So this is UTT minus C square Laplacian U f of xt with 0 initial values. Okay, so let's call this as 1. And a solution of this IVP1 is obtained by reducing it to an IVP with homogeneous equation and some spatial initial data. Okay, and that's what is referred to Duhamel's principle. Okay, so this is the related IVP. So consider this. Let me use this different notation. UTT minus C square Laplacian U is 0. So homogeneous wave equation. And where is this? So again Rn, not T positive but T bigger than S. Okay, and we prescribe initial conditions not at t equal to 0 but at t equal to yes. So ut xs, and this is given by f of x. So this one x is in R. Okay. So this is only a translation in t variable. So you just replace the formula by, so you replace t by t minus s. Okay, and this f is same as this f. Okay, so this. So now we are fixing this yes, so this is just a function of x only. Okay, and we will try to determine this solution for t bigger than s, and s is greater than or equal to 0, arbitrary, but for the time being it is fixed. So as we vary s, we get a family of solutions. Okay, so denote this solution by u of xt, and just to stress the dependence on the variable s, we also write this as u of xt. Okay, so for example, for n equal to 3, we have u of xts. Okay, so again read from the Kirchhoff formula. So here phi is 0 and psi is given by this function. So this go back, difficult to remember the constants. Okay, so here it is, for example, 1 by 4 pi c square t c square. Now we have to replace t by t minus s. Okay, and now this integral, there is no change there, so this is again surface integral. So this y minus x is equal to c t minus s. Okay, so wherever t is there, just you replace it by t minus s. Okay, so this is surface integral. So now this one is f of y s d s. Okay, so that is the surface measure on this sphere. Okay, so this is the solution of this auxiliary initial value problem. So from the given initial value problem, we construct first this one. Okay, a homogeneous equation, and the initial condition is coming from the inhomogeneous term in the original problem. Okay, so this, if you want to call it. Okay, so this is solution now. So this is again for t bigger than s. Okay, so what is the connection of this big U and our solution small u? Okay, so here comes the theorem. So this is Duhamel's principle. The solution of 1 is given by so u of xt is equal to integral 0 to t this xt yes, ds. So in the case of one-dimensional wave equation, we did in detail we verified that this is indeed a solution of problem 1. Okay, so similarly in this case also one has to do that. It's not immediately clear why this u given by this integral is solve the this problem. Okay, so inhomogeneous equation and with zero initial conditions. Okay, so you just try to look at the proof in one-dimensional case. So the verification, let me just write here, verification that U solves IBP1 was done for n equal to 1. The same procedure works. Okay, so when you are differentiating with respect to t, we have to exercise little caution because t is also in the integral limit and also it is in the integrand. Okay, so one has to differentiate uh, with care, but with respect to x there is no problem because there is no x in the integral sign, so that we can simply take the differentiation with respect to x straightway inside the uh, integral sign. Okay, so just let me just do that little bit. Okay, so for example here, okay, so sketch how you do that. So as I said, there is no problem with x variable, so you just take Laplacian u, simply 0 to t Laplacian u xt yes ds. But the capital U satisfies this homogeneous equation, so you immediately see that Laplacian u is equal to, so this is just 1 by c square 0 to t u of t t ext yes ds. Okay, and since now it is the two derivatives here, so you can just so similarly you can work out this u sub t, what happens to u sub t. So u sub t xt. So first you differentiate this t in the integral sign, and that produces, so u of xt T, okay, plus you have the other one, so ut of x t s ts, okay, and this one by the initial conditions, now this is 0 because you are taking this as 0, okay, when t equal to s, this is 0, so instead of s we have here tt, so this is just 0. So this is just 0. Okay. And the next one, so utt xt, and now this one is ut xt t plus 0 to t u sub dt. And this is where you get this f of xt. Okay. And this one, as we have seen already here, so this is just c square Laplace. And that completes the verification. Okay. So once we know how to solve a homogeneous equation, so it's not difficult to solve any associated inhomogeneous equation. Okay, so I have not written here the precise conditions on the right hand side, the forcing term f, but you can write down so what conditions we require in order that this u is a solution. Okay, so that's an exercise. Just okay. So write down the smoothness conditions on f so that u is a C2 solution. Okay. So with that thing, I will just conclude this lecture, and next time we will see another interesting application of the method of descent to telegraph equation. Thank you.